Good evening, Three Rivers Physics crew. Professor Martineau here, my lovely wife holding the video camera. So today what we're going to do, rather than me try to explain how to do this or have you follow along, I've made a video on how to do the lab that we're going to do today that reinforces the lesson that we just had on vectors and components. So this is a lot easier than me trying to use my writing pad, which again, my handwriting is already suspect on that, and certainly won't be able to get the point across for what I want for the graph. So let me set it up here, and then I'll tell you what you need to do. And all you need to do is follow the directions, and then you will do it on your own. You will again find the lab expectations are in the files for today, but you'll find this is a fairly straightforward lab. There isn't a lot of extra work that you have to do, but I am looking for, of course, accuracy. So starting off again, vectors are quantities of motion that can be expressed as either, as both a magnitude and a direction. The way that we graphically show vectors is with an arrowhead drawn roughly to scale. Remember, roughly to scale, with an arrowhead on it. The most important thing about the vector is the direction, right? You can't just draw a line segment. You have to show an arrow because a vector is defined by both its magnitude and its direction. And one of the things that we talked about tonight was the properties of vector addition, right? Following the rules for adding components. So remember, all vectors can be broken up into its subsequent components, and those components should be at right angles to each other so that we can kind of deal with vector addition easily. So the point of this lab is to really investigate the properties of vector addition, particularly when we're trying to add more than two components together to get a resultant vector, right? It's easy when there's two components because you just make a triangle. What happens when there's 10 components, right? That becomes a little cumbersome. But one of the things that we find out when we investigate adding components is what properties do vector
No.
what properties do vector addition. What can you do with vector components when you add them?
No, I think it does.
Does? Yeah, whatever. Okay, so I don't speak good English. So here's the deal. So that's what we're trying to do. We want to investigate what we can do and also show you that if you follow the rules of vector addition, it's very difficult to get the problems wrong. But if you don't follow the rules, you're probably going to get the problem wrong. So let's see what we need to do. So this is called the treasure map lab. And the reason we call this a treasure map lab is like with any treasure map, maybe you're given a map to go from the oasis to the sea and then east over to the shoreline. But another way that you could have a treasure map is that you could look at just a set of directions. So, and I remember this particularly from like old movies. They're like, okay, start at the palm tree, take 5 paces left to the park bench, and they take 4 paces right to the fire hydrant, then take 10 paces left and just follow the directions, and eventually you get to the treasure, right? So what we're going to do today is you're going to make your own treasure map. So what you'll need is the graph paper. You'll need a ruler. Potentially you'll need a protractor. If you don't have one, that's okay. You definitely need your calculator. And you need at least 2 different colors of writing implement. It can be black and red. It can be black and purple. It could be pencil and black. Optimally, you might need 3, but you at least need 2. Okay, so, and I don't care what the 3 colors are. Okay, as long as you have different colors. So I've set up my sheet here. So what you'll need is a piece of graph paper. And what we do to set up the graph paper is I've established the scale. So the scale here is 1 block equals 1 meter, just so we have reasonable units of measurement. We don't want to say 4 blocks, right? So we're just going to say that 1 block equals 1 meter. I've also established over here in the left-hand corner that up is the north direction. And now what I've done next is I have made a list of directions. So here's my list. And they are 1 meter north, 3 meters south, 2 meters east, 7 meters north, 5 meters west, and then 1 meter south, 8, 4 meters north, 6 meters south, 4 meters west. And what I'm going to do is, it doesn't imply, I didn't put it because I don't want to be too confusing, but I'm going to start, this is the first set of directions. This is step number 2. This is step number 3. This is step number 4. This is 5. I should have had this number 4. 6. This is 7, 8, 9, and 10. Now I have randomly chosen these. I don't have any set knowledge of where this is going to end up. But what I'm going to do right now is I'm going to draw these 10 directions in that order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to do it like the directions say. So each one of these is a component vector. And what we're going to do is we're going to add up all of these components to get a final resultant vector. All right. So here's how this is going to go. Right. So here's what you need to do. These are the directions. Need a ruler for a straight edge. You need to start in a spot with one color pen. So all of the components, all these components, I'm going to draw in black. Now it is humid and I'm left-handed, so I'm going to be smudging the hell out of this. For the record, that's not acceptable for you. Sorry, but you can't hand in smudged work. Also, to be clear, I have said before that I only want digital representations or digital copies of your work. You know, I don't want anything handwritten. In this lab, it can be handwritten. As long as it's neat, it can be handwritten because there's no point in doing this on Google Draw. So what I'm going to do is I'm going to start and follow the directions. 1 meter north. So I'm going to start down here, and hopefully it doesn't... whoa, shoot. Sorry. Hold on. Yeah. So what I'm going to do is I'm going to start down here with an asterisk, and I'm going to put start. And I'm going to draw 1 meter north, which is going to be this vector. So that's 1 block long. And I'm going to put an arrowhead on the end of that block. Okay? So here's my first one. The second one is 3 meters south. So I actually have to go against that vector. So remember, tip to tail, right? So this is the tail. That's the tip. The next one has to go on the tip of this vector. And now I need to go 3 units down. So back 1, 2, and 3. And now I'm there. Now I need to go 2 meters east. So I'm going to go 1, 2 meters east. Now I need to go 7 meters north. Notice I'm putting arrowheads after the end of each vector, right? So we went up 1, down, I think I did 3. 1,
yep,
2.
You did.
No, I did 4 actually.
Oh, you did 4.
Crap. All right, hold on. You can't do this, but I can. That vector should have ended there. Sorry about that. So up 1, back 2, 1, 2, 3 should have been there. And 2 meters east. So I'm going to go 2 meters east. 1, 2. Okay, there's my next vector. Now I'm going to go 7 meters north. So here we go. I'm going to go 1, 2, 3, 4, 5, 6, 7 meters north. There's the next one. Now I need to go 5 meters west. I think I've made a mistake.
Oh.
1, 2, 3, 4, 5. Yes, I have.
I think it'll work out because you're going to go...
No, because now I'm on the plastic bit.
Oh.
All right, hold on.
Just start in the middle.
I am going to start in the middle. Again, you guys, I need a neat copy from you. I misplanned. What you would do is you'd start over. Sorry. But now I'm going to start in the middle. I'm going to start over. So here we go. I'm going to start right about here. So we're going to go... So here's my start. I'm not going to put a big asterisk. So here's my start. I'm going to go up 1. And to be Bob Ross about this, you know, you can use any scale you want. It's your universe, you know, you can make... So we got 1 north, 3 south. So I need to go back 1. 1, and then 2, and then 3. And there's 3 south. Next thing I need to go is 2 meters east. So I'm going to go 1 and 2. There's 2 meters east. I'm going to go 7 meters north. 1, 2, 3, 4, 5, 6, 7. Oops, I should have done that. 1, 2, 3, 4, 5, 6, 7 meters north. I need to go 5 meters west. Notice they're all tip to tail. 1, 2, 3, 4, 5. 5 meters west. I need to go 1 meter south. 1 south. Then I'm going to go 8 east. 1, 2, 3, 4, 5, 6, 7, 8. 8 meters east. 4 meters north. I'm going to do all of them, folks. 1, 2, 3, 4. Okay, we're going to go 6 south. So I need to go back on itself. So we got 1, 2, 3, 4. 1, 2. So there's my 6 south. And then 4 west. 1, 2, 3, 4. And there's my end. Okay, so I would say by looking at it, I probably could have chosen a larger scale. But that's okay. That's the way it worked out. All right, I'm going to smudge the heck out of it. Now, so these are all of our components. So now what we need to do here is figure out, well, what's my resultant? The resultant connects the tail of the first to the tip of the last. So here's the tail of the first is right here. And the tip of the last is right here. So we're going to, in another color, draw a line that represents that vector. Okay? The next thing we have to do is, well, what's the length of that vector? Really, the only way we can do it is by trig. So I'm going to do the workout over here. Okay, so what's the length of this vector? So we're trying to measure the, you guys use S. So the resultant displacement. The resultant displacement is going to be the result of these two components. Look that this red vector is pointing up and to the right, and it's made of components that are 1 unit this way and 2 units up. So if I'm going to redraw this triangle just so I can see it, I've got, this is 1 meter this way, that's this vector, and I got 1, 2, 3, 4.
I use 3 squares.
I use 3? 1, 2, 3, thanks. 1, 2, 3, 4, 5, 6. I don't plan this very well. So, right, so this is 2 meters this way. And so we need to find out what this is, which is just going to be equal to the magnitude of S sub r will be equal to the square root of 2 meters squared plus 1 meter squared. And that will be square root of 5, which is 2.24.
Oh,
so
I was going to say 2.25.
I should have made this to 2 significant figures, so I'm just going to say 2.2. So this is going to be 2.2 meters. Okay. See, look, I'm smudging it. It's because I'm sweaty. I need the direction of this. So as we learned before, theta will be equal to, I'm going to skip a couple of steps here, tangent to the negative 1 of 2 over 1, right? Opposite over adjacent. So the arctangent of 2 is 63 degrees. And so if I'm going to report the actual vector, S sub r, resultant displacement, this will be equal to 2.2 meters at 63 degrees north of east. North of east. Now, if I'm going to critique my work here, I would have probably used a bigger scale so that we could see this vector a little bit better. Also, I had no idea where these were going to end up, these directions up here. I just wrote them randomly. And luckily, this is how it ended up. Okay, that the resultant vector, again, the distance and displacement from, the distance and direction from home is this vector, which makes up a triangle that's 1 unit to the right and 2 units up. So 1 meter east and 2 meters north. All I did was reconstruct the triangle here so you could see it. I did the math out and I got this. Okay, so now what your job is you need to do this map, but obviously can't use my directions. Okay, you're gonna make up your own, which I wouldn't think. That'd be a pretty cheap lab, just redo what I did, right? So you need to come up with your own 10 directions, map them out just like this. I'll be looking for the arrowheads. I'll be looking for the scale. I'll be looking to see if you're gonna use the trig. I'm looking for proper significant figures. So let's go ahead and say that each of these, let me make a note right now, you need 2 significant figures for all of your directions. So all that means is I should have written 1.0, 3.0, 2.0, 7.0. And it seems like, why do I have to keep putting 0.0? Because the answer has to be the 2 significant figures. So make those 0.0s. Now, that's the first part. You can come to me for this. In the second part of the lab, you need to get either another piece of graph paper, or if your graph paper is 2 sides, flip it over. You need to use the same 10 directions, but you need to shuffle the order. So rather than it going, if you want to come back, rather than it going, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you would go 1, 4, 3, 2, 8, 9, 10, 7, 6, 5. Any order you want. You just have to shuffle the order. Then replot your map with the shuffled order. Do the same thing with the displacements. Then do the same thing with the components. Draw your resultant in a different color. Determine the magnitude of the resultant using trig. Determine the angle of your resultant using trig. And then compare the result you get from the first map with the map that you got from the shuffled order. And then after that, answer the questions that go in the lab expectations. So you can come back to me. So that's generally it. So there's no reason, you have to do this by hand. The components all have to be in one color. The resultant has to be in another color. All of your vectors have to have the proper arrowheads on it. You need to show me your scale. You need to show me which way is north. You've got to do the map twice for your own set of directions. One, an original set of 10. Another one, a shuffled set of 10. But again, the same component vectors. Don't make a different map. Use the same components, but shuffle the order in which they're being added. And then after that, look at the lab expectations, right? There's a cover page, there's an abstract, there's some instructions about the two maps, and then there are conclusion questions that you have to answer properly, thoughtfully, in 6 to 8 sentences. And it gets at some of the properties of vector addition, okay? So that should be it. So you should, class ended at about 7:30, my guess. There's no reason you can't do that right now. I put a link to some graph paper in the files that I found, the PDF that I found. So if you don't have graph paper at home, you can certainly go print that out. Or if you don't want to look for it yourself, I made it available to you. Also, if you don't want to use the trig, and I didn't do this with this one because my triangle was so small, but if you have a protractor at home and you don't want to use sines and cosines and tangents to get the orientation of your resultant vector, you could use a protractor if you want to, that's fine. I don't know how you get the length of the vector, but if you want to use this, I'm saying that's allowable, okay? I will be in class in the meet till 9:30, so if you have any questions, you can certainly pop back in, but this should be a one and done lab. So, unless I hear from you, I will see you on Thursday at 5 p.m. So, thanks guys. Or, sorry, not Thursday, the next time we meet, so I could use this again. The next time we meet at whenever class starts. So, thanks. I'll see you next time.